Good afternoon, everyone. Welcome to another Atom seminar. Before we start, I would like to point out that this year the Atoms group is collaborating with the Laboratory of Complex System Engineering from Unicamp, led by Professor Luis Franco, to bring you the seminar with renowned speakers covering topics related to thermodynamics. Today, the Atom seminar has the great pleasure of welcoming Professor Jos Derksen. Professor Derksen is currently a chair in engineering at the University of Aberdeen in Scotland. He obtained his master's degree in mechanical engineering at the Twente University and his PhD in applied physics at the Eindhoven University of Technology, both in the Netherlands. He was also on the faculties of the Universities of Delft in the Netherlands, Alberta, Canada, and a visiting distinguished overseas professor at the Shanghai University of Engineering Science in China, and an adjunct professor at the Beijing University of Chemical Technology in China as well. His research interests include mesoscale simulations of solid-liquid suspensions, turbulent and transitional flow in process equipment, and multiphase lattice-Boltzmann simulations for liquid-liquid systems. Professor Derksen has also served as editor of the Canadian Journal of Chemical Engineering and of Chemical Engineering Research and Design. So once again, welcome, Professor Derksen. Thank you so much for being here, and please feel free to share your screen and start your presentation.
Thanks very much for having me in this seminar series, which I very much appreciate. I'm going to talk about flow, maybe a bit besides the topic that you usually have in this seminar, but I still hope that this is interesting and a little bit entertaining as well. So again, simulations of multiphase flow at multiple scales. I'm going to give some short motivation about what we consider multiphase flow dynamics, which is very broad, which includes things like blood flow, it includes sediment transport, it includes bubbly flow, so gas-liquid systems. We talk about emulsions as well, which are liquid mixtures, and the motivation is mainly in terms of chemical engineering processes. So we're dealing with collective behavior of multiphase flow systems, and we want to understand how that collective behavior, how process performance depends on what happens at the scale of the particles, where particles we consider bubbles, droplets, solid particles, any dispersion inside a continuous system. Okay, so let me just start with a typical example just to set the stage. Let me take a very non-woke topic of enhanced oil recovery, but in a sense an interesting example about multiphase flow. So what we're dealing here with is we're dealing with the problem of recovery crude oil from a reservoir. We need to mobilize crude oil, and one way to do this, you can see that on the lower left corner of this slide, is to inject water or to inject CO2 and see if we can get the oil, which is wetting the pore structure, if we can get that oil moving. And we have translated this problem into a very simple idealized system. So what I'm trying to convince you of here is that we have a liquid 2, which would be the oil immersed into a continuous phase liquid 1, and we generate a flow. And the simplest way to generate a flow is to put a plate on top of the system and to shear the system so that we generate the shear rate that we call G. What parameters are governing this system? The parameters are density, viscosity, surface tension, and some geometrical parameters. We keep things very simple. We keep the density of the two liquids the same. Rho1 equals Rho2. We keep the viscosity, nu1 and nu2 of the two liquids the same. And that allows us to determine, to calculate a dimensionless number, which is the capillary number. So the capillary number here is a ratio between viscous forces in the numerator and surface tension in the denominator. The second dimensionless parameter will be the static contact angle. So we define a contact angle theta here, where theta smaller than 90 degrees is a liquid 2 wetting the solid surface. Theta larger than 90 degrees would be a non-wetting contact angle. And we define a length scale as the radius of half the droplet in an unequilibrated state. So in a state where the contact angle would be 90 degrees. So this sort of sets the problem. The question is, as a result of the shear flow, is this droplet going to be stuck at the surface, or is it going to be sliding? Sliding is the desired situation, because that would mean oil recovery in the pore space. There's many ways to try and answer that question. And the first thing we tried was to do very coarse-grained elementary molecular dynamics based on Lennard-Jones interaction potentials, where we represent the two different liquids by tweaking this power 6 term in the interaction potential. So instead of the basic Lennard-Jones interaction potential with d alpha beta equal to 1, we are giving d alpha beta different values for the different liquid, and for liquid 1, liquid 2. If d12 is unequal to 1, we create surface tension, and we can create a contact angle by tweaking the liquid 1 solid interaction parameter, liquid 2 solid interaction parameter. All right. Then we do some calibrations in order to relate that the interaction parameter d alpha beta to measurable quantities such as surface tension. In the upper part here, we try and convince you that the droplet, the inside of the droplet has a higher pressure than the outside of the droplet, and then this enables a calibration of the surface tension through Young-Laplace equation. In the lower part, we show that shearing the surface gives rise to a shear stress, and then the shear stress gives rise to a viscosity as the ratio between shear stress and shear rate. And we can create droplets with different equilibrium contact angle by tweaking the interaction between the liquids, liquid 1 and liquid 2, and the solid surface. All right, so we now have, we started from Lennard-Jones potential. We used the interaction parameter d alpha beta to create contact angle and surface tension, and we have a viscosity, and then things look like this. So this is a brief animation where we start shearing the system. You see the droplet in white and the continuous phase liquid in red. The upper plate is moving in the right direction. That motion creates a shear flow, and the droplet, I'm going to try and show that again, maybe the droplet responds to that shear flow by not only deforming, but also seems to be sliding over the lower surface, which is actually standing still. We show more results on the further parts of the slide, where you can see that the deformation depends on the equilibrium contact angle, we see more deformation at higher contact angle, obviously. And if we increase the capillary number, which for the sake of argument would mean increasing the shear rate G in the system, we see stronger deformation for higher capillary number. All right, then the question that we try to answer is, do the droplets slide? And then the answer is yes. We can look at the footprint of a droplet. This is one example where we evolve in time from top to bottom, and you see a sliding of the droplet over the substrate. And that sliding goes hand in hand with a deformation of the droplet. What we then do is we plot the sliding velocity, the sliding speed, as a function of the capillary number and as a function of the equilibrium contact angle. Again, the capillary number is a measure for the shear that we apply, and we see a higher sliding speed for higher contact angles because the droplet is more exposed to the flow for higher contact angles, and we see an increase of the sliding speed with the capillary number. One interesting thing here is that we can identify a linear regime. So for some levels of the capillary number up to 0.4-ish, the sliding speed is proportional to the capillary number or proportional to the shear rate. So if we zoom in on that linear regime, then we can define a dimensionless sliding speed. The sliding speed made dimensionless with the shear rate G and the radius of the droplet. And then that dimensionless sliding speed is a unique function of the equilibrium contact angle with an obvious monotonically increasing relationship, because if the wetting state goes from wetting at low contact angle to non-wetting at higher contact angles, we see an increase in the sliding speed. Now, the question is, can we scale this up? Can we scale this up from a microscopic perspective, which is the coarse-grained molecular dynamics I have been showing, to a mesoscopic level? And for the mesoscopic level, one can use the Lattice-Boltzmann method. I'm not going to dwell much on the Lattice-Boltzmann method in this lecture. I would say that Lattice-Boltzmann method is a particle-based way to do fluid dynamics. Almost continuum, almost because still it is particle-based, an almost continuum way of doing fluid dynamics. Now, in the basic sense, the Lattice-Boltzmann method deals with single phase, only one fluid dynamics. We can, and there is lots of activity in this field, we can extend this Lattice-Boltzmann method to systems of immiscible liquids through phase field modeling and Kahn-Hillier type of thermodynamics. So what we do in multiphase, so two liquids, Lattice-Boltzmann method, including phase fields, is we have an order parameter that is switching between a certain minus, well, in this case, a -1 value, where we are in liquid 1. Remember the two liquids that we have, liquid 1 and liquid 2, red and purple, and it switches over a thin diffuse interface from liquid 1, phi is -1, to liquid 2, phi is 1. And that order parameter then satisfies an advection diffusion equation. The thermodynamics of the interface is brought in through a chemical potential and a free energy function that has two minima in the two different liquids. We then are able to create a certain interface thickness that we're going to call psi, and the surface tension gamma related to the kappa and A parameters that are defined in the chemical potential. The A parameter is here, the kappa parameter is over there. Now let's look at how we can do this sliding droplet problem in terms of a lattice-Boltzmann approach, and compare what we would find with and compare the lattice-Boltzmann approach with what we have achieved with the molecular dynamics simulation I showed you before. The system is defined here, and the devil actually is in the details. The devil is in the details. It comes to, I want to focus on the three-phase contact lines. So the lines where the three phases, solid, liquid 2 and liquid 1, where they meet. And the contact line properties are brought in through a gradient in the phase field parameter, the normal gradient to the wall of the phase field parameter. Now, what can we do in this respect? It is well established how to deal with an equilibrium droplet. We can achieve a certain contact angle through equilibrium boundary conditions. So we have equations, actually different equations from different literature sources that describe the normal, the phase field parameter, the gradient of the phase field parameter in the normal direction based on the kappa and A parameters and the desired equilibrium contact angle. We apply that equilibrium boundary condition contact angle, and we do again the sliding droplet simulation, the sheared droplet simulation, and the result would look something like this. So again, I'm going to show this again after it has finished. So what we do here is we start an equilibrium droplet, we shear the upper wall, we keep the lower wall fixed, and we see sliding behavior of the droplet based on a multi-phase lattice-Boltzmann simulation. Now, we can do the same thing. We can define a dimensionless sliding speed. The sliding speed of the droplet made dimensionless with the shear rate and the radius of the droplet, and we can plot that as a function of the equilibrium contact angle. And we see this behavior. So we see an increase of the dimensionless sliding speed with the equilibrium contact angle. We have here two sets of symbols that relate to two different types of equilibrium boundary conditions. They overlap very well. However, you can see that they poorly match the molecular dynamics results. So here I plot the lattice-Boltzmann results with the two different boundary conditions for the order parameter combined with the molecular dynamics results where the sliding speed, these are the black symbols, where the sliding speed is very much lower for lower contact angles, and only at higher contact angles there is some agreement between the lattice-Boltzmann simulations and the molecular dynamics simulation. So the obvious thing to now think is that, well, why would we use an equilibrium contact angle boundary condition in a clearly non-equilibrium situation? So that we have been investigating further based on a non-equilibrium boundary condition for the normal of the order parameter. In this paper of 2011, there is a proposal to come up with a boundary condition that looks like this. So it now involves the development of the order parameter with time, and it involves a parameter dw or dw star. dw is the dimensionless counterpart of dw star, with the problem that the order that this parameter dw is unknown. We don't know, and we don't have clear theory, at least I'm not aware of clear theory, when it comes to determining the parameter in the non-equilibrium part of the contact angle boundary condition. So what we did at this stage was first trying to find out if the non-equilibrium part, so the left-hand side of this equation, the non-equilibrium part of this boundary condition has an impact on the sliding speed. So what I'm showing here is for a specific equilibrium contact angle, how the dimensionless sliding speed depends, if and how the dimensionless sliding speed depends on the non-equilibrium parameter dw. And it does depend. The non-equilibrium part of the boundary condition changes the sliding speed. And an increase in the dw reduces the sliding speed. So what we then did was we used the molecular dynamics results for the sliding speed to come up with a fitted value for dw that gives you the correct sliding speed. And then we get something like this if we compare the lattice-Boltzmann simulations with the molecular dynamics simulations. Obviously, the left picture, where we show excellent agreement between the MD and the LB simulations, is a bit of a fake picture, because we actually fitted the dw such that the LBM simulations matched the lattice-Boltzmann simulations. At the same time, we now also can plot which dw is achieving a good agreement between is achieving a good agreement between the LBM simulations and the molecular dynamics simulations. So what we're doing here is we use dw as a fitting parameter. We see that for high contact angles, we don't need a non-equilibrium term. For lower contact angles, we do need a non-equilibrium term in the contact angle boundary condition. And this is pretty much where we are at this stage. So what we need to do, and this is an open question as far as I'm concerned, is we need to come up with some explanation or some theory on how to choose the non-equilibrium part in the equilibrium contact in the contact angle boundary condition for LBM simulations. All right, so this was an example of how to combine lattice-Boltzmann simulations and MD simulations to get a handle, to get some understanding of multi-phase systems, in this case, liquid-liquid systems. So I'm going to switch gears a little bit, and I'm going to talk a little bit more about liquid-liquid dispersion, so systems of immiscible liquids or emulsions. From now on, I'm going to stay away from solid surfaces. So I'm only going to look at at the basic events in this sort of systems when flow is involved. I'm going to look at breakup of droplets as a result of flow, or coalescence of droplets as a result of flow. Breakup is not that much of a challenge in terms of Lattice-Boltzmann phase field modeling. Coalescence of droplets is a very big challenge, in the sense that, remember, in the Lattice-Boltzmann method, we're dealing with a lattice, and the lattice determines the spatial resolution of the simulation, and you can imagine that coalescence put very high demands on the spatial resolution of the Lattice-Boltzmann simulation. Maybe that is clear from, maybe that gets a bit more clear from the example I'm showing here. So I'm now going to talk about coalescence of droplets. Again, droplets in shear flow. So we put two droplets, two spherical droplets initially in the sheared system. We move the upper plate to the right, we move the lower plate to the left. We then produce a certain shear rate that again we call G, and we give these two droplets a vertical offset that we call delta Y. And we change the capillary number. And we look at simulations of coalescence, or in this case, not coalescence. So this is at a relatively high capillary number, a relatively high shear rate. If we lower the capillary number, we get coalescence. And lowering the capillary number here, but not definitive coalescence, it is a temporary liquid bridge is being formed. Only if we lower the capillary number a bit further, we actually see coalescence between the two droplets. And I'm quite sure you can understand the dependency of the capillary number in this respect. Let's focus on the situation where we change the capillary number with the shear rate. Then a high capillary number means a high shear rate, meaning a low contact time between the two droplets. And there is not enough time for the film that forms between the two droplets to drain, and therefore we don't have coalescence. We do have coalescence if we give the system a bit more time. As you can see here, this seems a bit like an unlikely coalescence scenario, but as you can see in the image right here, an experimental image, here we see the same scenario of coalescence, two droplets approaching, and then upon separation, only upon separation, they form a liquid bridge and they coalesce. This is at a relatively high offset between the two droplets. So the droplets are in the streamwise direction pretty far apart. We have done simulations in much lower offset. So now we're talking about an offset of 0.2. And when the offset gets smaller, the demands on the simulation get larger, because, and I'm going to play this movie again as well, you can see that resolving the film, the liquid film between the two droplets, is going to be a very challenging issue here. So what I've changed here was the vertical offset between the two droplets. I'm going to show that again, and you can imagine that we need very high resolution in order to represent the film flow and the rupture of the film flow. So it is time to think a little bit about length scales at this stage, because I have only been talking about capillary numbers and contact angles, that is dimensionless quantities, it is useful to think about how big these droplets actually are. We don't know, but we have some information, there is experimental evidence out there that critical film thicknesses in liquid droplet coalescence are of the order of 30 nanometer. So critical film thickness, if the film gets thinner than 30 nanometer, it ruptures and two droplets will coalesce. So what I'm plotting here is a few coalescence or non-coalescence scenarios. So here we're plotting the film thickness that if non-coalescence occurs, it decreases, no coalescence, and the droplets separate and the film increases. And then at a critical capillary number of about 0.2 for a system like this, we see the critical film thickness in lattice units of about 5. So the conclusion of this analysis is that that 5 lattice units represents roughly 30 nanometer in physical space, meaning that our droplet has a radius of 200 lattice units. So we're talking about a 1.2 micrometer droplet that we sort of confidently can simulate coalescence of. Conclusion from my point of view is that this is a bit of a hopeless situation in the sense that we can resolve films for 1.2 micrometer droplets, but in practical systems, in practical chemical engineering systems, droplets are much larger, usually millimeter or even centimeter size. So phase field methods are not that realistic when it comes to determining coalescence behavior of droplets or bubbles. All right, I'm gonna skip over charged droplets because I'm running a bit slow. So let me remind you of the narrative that I sort of try to give you. I started talking about multi-phase flow, then I talked about liquid-liquid systems on substrates, molecular dynamics, and Lattice-Boltzmann methods. Then I talked about immiscible liquids. So now we're back at multi-phase flow, and the last 10 or so minutes, I would like to talk about solid fluid mixtures. So instead of liquid-liquid mixtures, solid fluid mixtures. And one of the motivations here is fluidization. So many chemical processes for contacting solid and liquid or solid and gas use fluidization units, which can be huge meters, tens of meter size units. Their operation is very simple. What people do is they put fine particles, powders in a gas flow, a fluid flow, or a liquid flow. They make an upward fluid flow, and in that way they have intensive contact between solid and gas or solid and liquid. And fluidization, if you think about it, is pretty much the same as sedimentation, only a different perspective. Structures in solid fluid flows are intriguing. So you almost never have homogeneous solid fluid flow. They always form, unless the particles are very fine, they always form complicated structures. And these are at 3 levels of enlargement. These are experimental movies with courtesy from the National Energy Technology Lab. This shows the complexity of solid gas systems, fluidized solid gas systems. And we want to mimic this sort of behavior. We want to understand, we want to mimic this sort of behavior at the microscopic scale. So at the scale, the finest scale we see here, we want to be able to simulate the interaction between fluid and solid at the scale of the particles. That works quite well. So what I'm showing here is an example of an experimental system where you can see here the individual particles. These are motion blurred particles because the speed is very high here, relatively high here. And what you see here is that the system creates voids. So open spaces that are almost void of particles. And if you look carefully, you see a zigzagging motion of these voids. And these we can mimic quite well in a detailed simulation. So you see here the same void, only one void, given the size of the system, meandering through the fluidized bed with conditions, that is density and viscosity and density of particles and liquid and viscosity of the liquid, very much the same, very comparable to the experimental picture. So I won't dwell very much how we do these simulations. The important message that I want to give is that we do what's called particle resolved simulation. So we make our computational mesh on which we resolve the fluid flow. We make it finer by at least 1 order of magnitude than the size of the particles. It means that we don't need it don't mean that we need strong modeling of forces on particles. We actually resolve most of the forces and torques on the particles. And such an approach allows for changing the shape of particles. Since we resolve the no-slip condition at the surface of the particle, we can resolve the no-slip condition on particles of shape different than the usual spheres that people do simulations about. Some painful algorithmic issues relate to collisions between particles. We use quaternions, which molecular dynamics people know very well, in order to keep track of orientation of particles. And I'm going to show you quickly some results on fluidization with cylindrical and spherical particles, where I'm comparing here the side view of a fully periodic fluidized system with a cross-section, which shows the strength of numerical simulations that you are able to really look into the system and see an instability occurring here in this mixture of spherical and cylindrical particles. And that structure disappears largely when we change the aspect ratio of the cylindrical particles. So the same particles, the same volume per cylindrical particle, but a higher aspect ratio. Finally, I want to talk about hollow particles, because hollow particles are used in structured catalysts to enhance mass transfer. So what we did is we did simulations of fluidization simulations of hollow particles that if you resolve the particles, that works in theory. And then the interesting thing is, can we determine the mass transfer inside these hollow particles? We can determine the flow inside the hollow particles. It looks like a Poisson flow inside the particles that goes in different directions dependent on the orientation of the particle relative to gravity. And if we assume Poisson flow inside a pipe, inside a cylinder, we can determine the mass transfer coefficient through what's called Gratz solutions for the Sherwood number, where the Sherwood number is the dimensionless mass transfer coefficient. I'm not going to dwell on this very much because I'm really running out of time. the final result is a Sherwood number, an average Sherwood number of a fluidized bed as a function of the Archimedes number being a measure for the strength of fluidization. All right, so I'm gonna stop here, putting up this slide with the question, is there anything worth remembering? Well, I leave that up to you. A few items I would like to summarize here. Sliding droplets and the effect of the sliding speed. And the question if a moving three-phase contact line is actually a molecular phenomenon. Diffuse interfaces for simulating liquid-liquid systems. And the question is if we can ever reach grid independence given the level of detail for, at least for coalescing systems. And then I talked about solid liquid systems where it is important to capture the shape, the role of the shape of the particles. And in general, I think it is very important. I did not show much experimental work other than from literature. I think it is very important to ground simulation work in experimental validation. So with that, I would like to stop here by thanking you for your attention. And I sincerely hope that there are items for discussion.